review tomorrow because we worked hard this week. And then, did I tell you that Monday is going to be multiple choice Monday? No. We're going to be doing multiple choice Monday, every Monday, to get multiple choice practice in because we need to make sure we're getting that as well. So that is the plan for the next couple days. Okay. Let's roll. Let us roll because we have to. Unit 2, types of chemical bonds. Types of chemical bonds. What were the two main types of chemical bonds we learned about this year? Ionic and covalent. And then did we learn if those actually exist?
Yeah.
They don't really truly exist. A true ionic bond would be what? Between what and what on the periodic table? Francium and fluorine. Because in order for it to be truly ionic, you have to have a huge difference in what? Electronegativity. Look at the segue I just gave. Man. What is the periodic trend? That was actually kind of good. It's like I planned that. What is the periodic trend for electronegativity across a period? So as I'm moving across the period, what happens to my electronegativity? It should increase. It should increase across the period. What about down a group? It should decrease. We've talked about this. So when determining your change in electronegativity, what range would constitute the formation of a nonpolar covalent bond? Okay, well this isn't something you have to have memorized, but a true nonpolar covalent bond, what was our example of an actual covalent bond? Thank you. What? Diatomic elements, yes. So in diatomic elements, if I had the same and the same, what's that going to be? What's the difference going to be in electronegativities? Zero. The actual number is less than 0.5 difference.
What is delta here?
Delta, change in electronegativity.
Oh.
Less than 0.5. A polar covalent bond is anything between 0.5 and 1.7. Remember the chart in the book that listed out all the electronegativities? Mm-hmm. It was like the periodic table, but with electronegativities.
Oh yeah.
Yes. Correct. They got bigger, showing their size and their electronegativity. An ionic bond is greater than 1.7, so more than 1.7 difference. So, why does electronegativity increase across the period? Well, we know, moving across the period, what's staying the same?
Shells.
Shells / shielding is constant across the period. I'm going to Beef O'Brady's tonight, having a guys' night, and we're going bowling.
Oh wow.
Very excited. I haven't been bowling.
Is surprisingly good.
I know.
It's like actually good.
Has anybody here not been to Beef O'Brady's? I actually recommend it. I agree, Maggie.
Like I was kind of suspicious of it at
Their wings are good. Their appetizers are good. Their burgers are good. Yes. Like, it's better than Applebee's.
Yeah.
It's like real food.
Yeah. It's like a real food.
Yes.
Applebee's had unlimited boneless wings.
I went to Applebee's.
That was crazy.
Oh. Is that what gave me a seizure? No.
That's not a good decision.
Because I went to Applebee's when they had the all-you-could-eat. It was like wings, fried shrimp, and something else. Me, Melrose, Ruff. It sounds like something we would do.
Applebee's, that's asking.
I know. It is. No, it wasn't that day because it was a work day. So it must have been a Friday.
Yeah.
I'm not sure when it was.
Like,
I think it was the Friday. Applebee's, the 5 cheese mac and cheese chicken tenders that comes with a breadstick.
Yeah.
Anybody got that before?
Yeah.
It's like mac and cheese with like a honey glazed boneless piece of chicken and then a breadstick.
It's good.
Get it every time. Applebee's also has 3 of the top Dew brews in the city, so Mountain Dew at Applebee's, real good. Real good.
McDonald's Sprite. McDonald's Sprite.
Well, they've actually tested McDonald's, and the water's filtered differently at McDonald's, so like Coke and Sprite literally taste better at McDonald's.
I knew it.
It's scientifically proven. So, anyways, shells and shielding is constant, but my core charge is doing what as I move across? Increasing. So if I have more pull in the middle, that's going to create a greater what? Desire for electrons. Okay. What type of bond will form in each of the following combinations? We should have an electronegativity periodic table, but let's try to guess. We can probably guess. CaCl, ionic, polar covalent, or covalent?
Covalent.
CaCl, ionic.
Oh, that was another CL.
Chaz.
Ionic. CO.
Polar.
So if you think about it, like carbon is almost at the end of the gain of the losing, right? And oxygen's at the beginning of the gaining. Polar covalent. Polar covalent. Polar covalent. OO. That's going to be
Gonna be
nonpolar. Nonpolar. It's technically nonpolar covalent, but if you say nonpolar, that's fine. What about HO? Polar covalent. ALP? Those are pretty close to each other on the periodic table.
Carbon and oxygen.
But Al wants to lose 3 and phosphorus wants to gain 3. Polar covalent. NAF? Ionic. That's ionic. You don't have to memorize those numbers, but it's just talking about what's the difference between polar covalent and ionic. Guys, I stapled this one better. What type of ion is formed by metals? Don't overthink this. Cation, which is positive. Nonmetals is going to be my anion or a negative ion. What type of bond is formed between a metal and a nonmetal? Ionic. So use words to describe each type of bond, then draw a particle diagram that represents each type of bond. So how would you describe an ionic bond?
A bond?
Electrons transfer, I like that, or donated.
Can you say because of a large difference in electronegativity?
You could. Electrons transferred or donated, and there is a positive and a negative ion. What about covalent? Sharing electrons. Sharing is covalent. Yes?
Yeah.
Metallic.
Ooh, I'm
Oh, metallic metal carrier. So this is when like it's the delocalized sea of electrons, isn't it?
It's like electron clouds, right? That are, I love the word delocalized. Because these electrons can flow across the surface of the metal, which is why metals are what? Conductors. Which is also why metals are malleable. Boom. Megan on fire. Did I hit record? I did. We're good. Draw. So draw a, who you shouting out?
Gianni.
Oh, make sure you say it loud enough. Okay. Draw. Why don't you guys, how would you guys draw a ionic compound?
Like
Big
one plus,
big one, little one.
Which one's big?
the anions.
Frick, I always mix that up.
Bruh.
Negative's gonna be big, right? Because it gained an electron. If it gains an electron, what do the electrons do? Repel. Positive's gonna be small.
What is that? Aubrey, let me see it. Aubrey, let me see it. Aubrey, what is that?
Covalent.
Two similar signs. Doesn't
Yeah.
matter what charge they are. Well, actually, it should be negative, right?
They'll probably be both negative.
Because it's normally with nonmetals.
Yes. And then what about metallic?
Just a bunch of pluses.
So you have this, and in between, you have those negative electrons kind of flowing in between those. That sea of electrons that flow through. How does, oh shoot, we got ahead of ourselves. How does a delocalized area contribute to the properties of metals? Well, metals are what?
Malleable.
Yes. They're malleable, they're conductive, they're ductile. I don't know.
Does ductiles mean you can stretch them?
Ductile means you can stretch it into a wire. It's a different way to describe malleability. Because electrons,
Why does that make it no?
because the electrons aren't in locked positions.
So that's,
They're flowing across the surface.
I'm also not.
So I'd say
I just had an aha moment.
electrons are not locked. The electrons are not locked. Therefore, they conduct. It's malleable. It's ductile. Cool? All right. Flip it.
Oh, it's so much nicer.
Okay. We might finish this in one period. I'm not sure. Okay. Label the following on the graph above. So this is talking about where a bond forms.
Yeah, I remember this. They want to form at the minimum value.
Right. So you're going to label 3 areas on this graph: too close, too far, and optimal distance. So label those points.
Oh, I remember this.
By the way, so like one point is going to be here, one point's going to be here, one point's going to be here. So label each one of those as one of those 3 choices. We're doing great reviewing pace. It's good.
I remember this. Just the funky graph where if they got too close, they were pulling each other, but if they were too far away, they had to track each other. So they have to find a gap.
What'd you guys label this section?
Too far.
Too far. What did you label this section?
Too close.
Too close. And what did you label this section? Baby bear.
Goldilocks zone.
Just right. Right? Perfect distance. So if these are too close, what's going to happen at this section?
They're gonna repel.
They're going to repel. If these are too far, they're going to want to not attract. And if they're right here, what are they going to form? Form a bond.
It's always like pico.
They form a bond. Yep, this was measured in picometers. Form a bond. Okay. Number of bonds. Bond length. What did I teach you about bond length and bond strength? Thank you. Let's write that down. The shorter the length, the stronger the strength. I don't know why, but I've been like a little emotional today, just in the back of my mind about the year coming to an end.
We have to make
I
a shirt.
accidentally voted.
I know. Has anybody worked on the shirt idea?
No, because we need to have it for the AP test.
we have-
We should all wear it
That'd
on
be
the.
sick.
So here's the thing.
Oh, we can't have anything that.
You can't wear it on the AP test.
Boy,
I looked that up.
Has stuff
If there's
on it.
anything scientific, it's not allowed.
that one shirt.
What shirt?
But we have, who has the picture of it?
What do you mean the
Who was going to work on coming up with something?
We had the
So, didn't someone take a picture of it? I was going to make something on Canva?
Yeah.
Who had that?
Way.
Well, I mean, I think someone else had it. Maggie and Joey.
Wasn't it Maggie and Jawe?
Joey, somebody's got it.
We can get it back.
Yeah, we'll get it.
We'll get it back.
Oh, where's the?
Shorter the length, stronger the strength. Anyways, I was just going to say that, like, I'm going to miss you guys, is what I was going to say.
Mr. Eller, I'll miss you, but I don't think I'll miss.
It's okay.
I'm not gonna miss Woodstock High School.
But, like, this,
Cap and gown.
like, cap and gown tomorrow.
Yeah.
All right.
I might actually cry at that.
I mean, I have 3 people in here that I've got to teach 3 years in a row. Like, that's super odd that that can happen. So,
I was in
oh, you're right. I didn't have Megan last year. Never mind.
Ruffs was so.
It's okay.
2 people.
Ruffs was
2 people.
Scary.
Hey, I think they're
Yeah. But freshman year, was that COVID? Yeah, so that was kind of,
Hey, you technically have me.
Oh, you still
That's
went
true.
to the labs
yeah, we still did the fun stuff.
for AP physics students.
Oh, yeah.
We did
I remember
rockets.
that.
I did my rocket. Aubrey didn't remember, so I was listening to
Oh,
that is right.
This is the second time in my career where I've got to have people 3 years in a row. The first time was my first 3 years.
I've had birds on.
Because my first 3 years I taught physical science, and then I taught biology. And then, like, obviously I was good at chemistry, so then I got a chem class. So I got some of those people the 3rd year in a row. So,
Honorary.
okay. Well, Megan, you sent me enough emails that it was almost like, all right.
This is true.
Bond length. Here we go. Bond length. Single bond. Long, short, medium. This is the longest. Double. Mid.
Intermediate.
Triple. Short. Bond strength. Weak. Mid. Strongest. And if you guys remember when we did like the models, right? The single bond was like this, right? The double bonds were like curved in. And then the triple bonds were even closer.
I remember that.
Yep.
Triple ones like almost are they rare? Triple ones.
Not necessarily, but like you're only gonna get a triple bond from like diatomic nitrogen or phosphorus, something like that. All right. Graph on the right shows potential energy and distance between the imaginary molecules A, B, C. We did this on the test. Which molecule has atoms that are closest to each other? A2, right? Please say A2.
What's the reason?
What's that? Well, because the distance. It's just literally, it's the farthest to the left.
I predicted the next
Which molecule has the greatest potential energy in its bond?
C, because it's got the greater dip.
C2, biggest dip.
Big dip vibes. Big spin vibes.
Which molecule requires the most energy in order to break the bond?
A. C, because greatest potential.
Greatest potential energy.
Well, I'm about to get
Hello.
Does anyone else Detroit like?
No.
Like where you do the simple circuit?
We're putting you on.
No.
Getting the earbuds, getting the wax earbuds out.
Okay. One of these molecules has a single bond, one has a double bond, one's a triple bond. Which molecule is most likely the double bond? It's the middle. B2. Circle the correct words. As atomic radius increases, core size
Increases.
increases.
Core size is the size of the nucleus.
This causes the bond length to
Increase.
increase.
Oh.
If the radiuses are bigger, right, they're going to be farther apart, which leads to a blank in the bond strength,
Decrease. Oh, this is why the smaller atoms have the stronger. Oh, yeah.
which leads to a
I have a question.
decrease in the bond strength.
Are
Yes.
the bonds from like the outermost electron or like the core of the like the atom?
What?
One measure. If you measure bond distance,
Is like does the bond start from like the two outermost electrons or does it go like to the inside?
Temperature.
So, Aubrey's asking a pretty complex question here. So, the bond length is measured from nuclei to nuclei. That's what the bond length is being measured. The rest of it's kind of theoretical. Okay. For each of the following, circle the atom with the smaller atomic core, Na or Br.
Oh, it ain't. Where's BR? Where is BR? Chad, where's BR?
Yeah, BR's all the way over there. There's no way. It's an
Where?
no, but BR is a step lower.
It's
BR is a lot further to the right, but it's also a lower
One
down because
down.
it has an extra
So,
energy.
N.
Yeah, but BR is a bigger molecule.
Exactly.
That's why it has the bigger one. It's the circle the smaller one. It's NA.
Mr. Heller?
Chat?
Are we cooked?
I need to think about this.
Oh.
Oh.
We have to look at the values,
Well,
right?
then I guess I'm not gonna get it right.
So, Na,
Oh.
Maybe. I just need to find the shirt.
we're talking about atomic core.
This dumb little like chemistry shirt.
Oh my god, you nerd.
Na wants to do what with one electron?
Give it away.
Give it away. Br wants to do what with one electron? Gain an electron. I'm trying to think how we can answer this.
Okay, move on.
Chat, what's an atomic core? We just size of the nucleus? Yeah, yeah, anything small. Because there's less protons than neutrons.
I'm just gonna make sure we're just doing this one right.
Chat?
This is smallest what?
Atomic core.
Atomic core.
Okay, is the packet pulling a fast one on me? Because I'm pretty certain I'm right.
Is it pulling up fast?
What are you looking for?
Maybe sure.
What day is it?
I don't know. I sent it to you. I thought.
Oh god, no, put it away.
All right, I'm gonna plug this in real quick. This is what I thought. This is what I thought. I'm gonna switch over to this. Here we go.
Alright, what's the answer? So it's gonna be,
Hello.
no, it's gonna be BR.
It's bromine.
You guys are actually so dumb. Come on.
No one is dumb.
It was just a joke.
All right.
Don't take offense.
So atomic radius, atomic core, sodium is going to be much bigger. First of all, because it wants to do what with one electron? Lose. And
So
then,
it's repelling more.
yeah, and also as you get to bromine, right? Bromine has a lot more what than sodium?
Proton.
More protons, which is going to pull it in more.
Atomic radius isn't, or atomic core isn't
It's the same thing.
the same thing. What?
Atomic core, atomic radius is essentially the same thing.
Oh,
So it's bromine.
I thought not even that bad. I thought he was talking about the size of the nucleus specifically.
Yeah, but when have we ever talked about like the size of the nucleus?
Never.
Okay. CS or CL?
CL.
CL.
Definitely
CS. Yes.
CS is bigger.
Yeah, but
CS is massive.
well, the smaller one. Yeah, so it's
CS has way more levels of shielding.
Oh, I thought you said CS.
So CL,
Everyone needs a gummy.
smaller atomic core, carbon or oxygen.
Oh, it's smaller.
Oxygen, and then CL or AS. It's going to be CL.
One down, two left from CS.
Wait,
Yeah, it's
CL or AS?
a little table.
Yeah, it's going to be CL.
Good job, team.
So, there is
Draw a particle diagram.
that.
That's just, you gotta just do head on, head on.
It's like the dots with the
Okay.
little line there.
Draw a particle diagram for the ionic solid LiF. Your diagram should go to scale, and you should include the charges of each particle.
How many particles?
Let's do 6 total particles. So draw it with 6.
Oh, good.
Oh, we need to make a difference.
Oh, right.
No.
Mind your business.
I did.
Oh, it's a solid.
I did.
No, I did the exact same thing.
That's what I meant, they were only F's.
I did.
Okay, well, I said negative and not.
Yeah, but that doesn't distinguish.
Is it okay if we draw it horizontally?
If you just wrote negative, positive, yeah, it doesn't matter. If you just put negative, positive, they're just +1, -1. As long as you made the lithium small and the fluorine big.
Does it have to look like that exact?
No, it does not. That's just how Joseph drew
Might
it.
have a little bit too much space in between.
Why are the particles arranged the way they are in this structure? How will they organize?
Lattice.
Why?
That's how solids are.
Lattice to minimize what? Repulsion. Repulsive forces. And maximize what? Attractive forces. So a lattice to minimize repulsion and maximize attraction. How many pages have we done so far?
Like four.
How many pages are there? Because I want to do half. 2, 3, 4. We've done 5, count front and back.
6 left.
So we need to do one more page.
Oh, thank God, we left off the Lewis.
All right. Give an example of an interstitial alloy.
Oh, no.
Oh, this is one. This is one of the different sizes.
So if I have like these big ones,
There's a little one in between.
you got it. You got the little ones in between.
Anatomy.
Oh, because inner means between.
What's an example of an interstitial?
I'm just gonna choose two random metals. Manganese and tin.
I was thinking of steel.
Oh, well, you know, I guess.
Maggie.
So carbon would be the tiny one and iron would be the large one.
You sound like Farrah.
So carbon would be big. Iron would be small. And then what about a substitutional alloy?
They're all the same.
They're all the same, but some of them are substituted in, right? All the same size, but some of them have been subbed in with something different. So something like that. Example of that.
Like.
We just did this. Brass. Brass. So this could be like tin/zinc. What?
What is the right answer to steel?
Carbon big, iron small. Carbon big, iron small. So that leaves 1, 2, 3, 4, 5, 6. Yeah. Let's stop there, and then you guys can use the rest of the period to work on FRQs. Or finish your
Yeah, I did that last night.
or finish your unit 1 second half.
Oh, I did that. Can I just